present the fractional Fourier transform. So to start, we showed in class that the regular Fourier transform is a function essentially from L2 to L2. What that means is that we can compose the Fourier transform with itself. We get f composed with f of some function f of t. Now we might write this as the Fourier transform squared of a function f of t. In general, we can extend this notion to any integer n. We can compose the Fourier transform with itself n times. As I think we showed in class, this is a cyclic thing. You end up just going around in circles, as it were. Now, what the fractional Fourier transform is, one way of thinking about the fractional Fourier transform is that this integer n is just extended to a non-integer, to any arbitrary real number. Now, how do we do this? Well, if we had a linear transformation, a matrix, a finite dimensional linear transformation, we might try diagonalizing it. So you might say, oh, we can write m equals v d v inverse, and then m to the alpha, where alpha is some real number, equals v d to the alpha v inverse. So essentially what you're doing is raising the eigenvalues, because that's what's on the diagonal, to the real thing, to the real parameter alpha. We can essentially do that with the Fourier transform. Since it is shown that the Fourier transform has a countable orthogonal set of eigenfunctions, which are sort of a family of curves similar to the Gaussian. Which we call psi sub n, where f of psi sub n equals lambda n psi sub n. Now, because they're orthogonal, we can express any function f as a linear combination of these basis eigenfunctions. Equals the sum from 1 to infinity of some constant a sub n times the basis function psi sub n. Now, because they're orthogonal, we can extract a sub n purely through taking the inner product. So that just take the inner product of f with, so that's f of t times psi sub n of t dt from minus infinity to infinity. Okay. All right. Now, if we want to calculate the fractional Fourier transform of f of t, we just say, well, we just raise the parameter lambda sub n to the alpha in front of each term. So this just equals the fractional Fourier transform of the sum of a to the n psi sub n. And by linearity, that just equals the sum of a sub n lambda sub n to the alpha psi sub n. Right? Now we can replace a sub n with this thing here. So we get this equals the sum of the integral from minus infinity to infinity of t times the eigenvalue to the power times size of n of u for a different variable. Yeah. Now, you can rearrange this integral. You can rewrite this as a purely integral transformation. So we have this just becomes f of alpha f to the alpha rather of f equals the integral of f times this nasty function, which is this infinite sum of the eigenvalues times size of n of t, size of n of u. Alright, and then dt. So just as the Fourier transform is defined by the transformation kernel, by the function inside the integral, the family of functions, so is the fractional Fourier transform. And deriving the fractional Fourier transform is all about figuring out what this guy is. Now it turns out the eigenfunctions of the Fourier transform are very well known, and basically it becomes a really horrendous computation to figure out what this infinite sum is. But I think I have a better way of doing it. And for that, we're going to look at the time frequency plane. The time frequency plane can be sort of thought of as a collection of short time Fourier transforms. We have time here and frequency here. So a complex exponential always has the same frequency at all times, so it's going to look like this. Horizontal line. A delta function in this time frequency plane has it's zero everywhere except for at one point t naught where it has an equal representation of all frequencies. So it's kind of like a vertical line. Thus, in this time frequency plane, so the delta functions, the set of all vertical lines, are the transformation kernel of the identity transformation. To get from the kernel that represents the identity transformation to the kernel that represents the Fourier transform is a 90-degree rotation in this plane. Thus, one way to approach the fractional Fourier transform is to say, what if we use the kernel given by an arbitrary rotation of the delta functions? And that's exactly what we're going to do. So, we take a function and we rotate it through angle alpha. We take a delta function and we rotate it through angle alpha. Now, basic trigonometry, if this is length u here, we have u cosecant alpha is the height here, and the slope is minus cotangent alpha. Now, how do we represent this function? How do we represent the formula for this function? Well, if we think of frequency as the rate of change with respect to time of the phase of a function of the form a e to the I f of t, then frequency is f prime of t. Right? Now, what we know about this function is that the frequency at time 0 is u cosecant alpha, and that the frequency changes at a rate of minus cotangent of alpha. So that means that f prime of 0 equals u cosecant alpha, and that f double prime of t equals minus cotangent alpha. There's the simplest way of solving this system is just to say, well, why don't we let f of t then equal u t cosecant alpha minus cotangent of alpha times t squared over 2. That satisfies those two things. And thus, we have a first expression for the kernel of our transformation. We're actually very close to we're 90% of the way to the fractional Fourier transform already. So that is that this function equals some constant times e to the I ut cosecant alpha minus cotangent alpha t squared over 2. And now all that's left is to find this constant. And how do we find this constant? Well, there's a couple things we know about this from our formula that I already erased. We know that the kernel is symmetric in U and T. This isn't symmetric in U and T, so C has to take care of that. We also want it to be a unitary transformation. We don't want to change L2 norm, so C has to take care of that. And we also know that for alpha equals 0, we want the identity transformation. So we want this to become a delta function when alpha equals 0, so C has to take care of that scale. In the paper, I go through the detailed derivation of what C has to be using those three facts. And what you see is that to make the function symmetric in U of t, we add on a term of, we multiply by a factor of e to the cotangent alpha u squared over 2. So what we have is e to the I cotangent alpha times u t minus, that's cosecant alpha, minus cotangent of alpha times u squared over 2 plus t squared over 2. And then in front of this, the constant that makes it a unitary transformation and preserves and gives us the right phase so that it converges to a real delta function as alpha approaches 0. We have a factor of the square root of 1 minus I cotangent alpha over 2 pi. So this is the kernel of the fractional Fourier transform. We can call this b sub alpha of u t. If that's the case, then we can write the fractional Fourier transform. The fractional Fourier transform is simply the integral of our function. Fractional Fourier transform is just the integral from minus infinity to infinity of f of t times b of alpha u t dt. And that's our fractional Fourier transform. Now, there's also the discrete version of the fractional Fourier transform. It turns out you essentially do a similar process to how we started out. You diagonalize the DFT matrix, then simply raise the eigenvalues to the power of alpha that you want to get some sort of intermediate value of the transformation. Now, it turns out you have to be very careful how you diagonalize it to get something that approximates the continuous one very well. And that's the subject of an entire paper that I read. and I implemented their technique. And what we can see is the continuous deformation of a square wave into a sink and back. So, here we have a square wave. The parameter I'm sliding is the fraction of the Fourier transform that we're doing. So we're going to slide all the way to 2, which will be 2 Fourier transforms, so we should sort of get back to the square wave. And it is shown that as you vary alpha, the output of the fractional Fourier transform does change continuously. It's a continuous deformation, and there we're at a full Fourier transform, and we've gotten to the sink function, and then we slide back into a square wave. Now, it is shown in the papers that the fractional Fourier is continuous with respect to alpha. Now, one of the things I investigate in my project is whether or not it's differentiable. And it turns out it is. However, the derivative of the fractional Fourier transform with respect to alpha ends up being expressed, it's messy enough that I'm not going to write it down here, but it ends up being expressed as you've got a constant 1 times the fractional Fourier transform of f. So this is the derivative with respect to alpha of the fractional Fourier transform. Constant 1 times the fractional Fourier transform plus another constant times the fractional Fourier transform of t times f of t plus a third constant times the fractional Fourier transform of t squared over 2 f of t. Now, what does this tell us? On an unbounded domain, the Fourier transform of t squared, or even t for that matter, doesn't converge, because the functions blow up as they get to infinity. So, even though the Fourier transform is well defined, and therefore, as is shown in many papers, the fractional Fourier transform is well defined and converges for these functions. Not only that, it's continuous with respect to alpha, the fractional Fourier transform. For a function like f of t equals 1, which Fourier transforms into the delta function. For this function, even though the fractional Fourier transform is continuous with respect to alpha, because the derivative with respect to alpha depends on the fractional Fourier transform of t times f of t and t squared times f of t, neither of these converge. Therefore, even though it's continuous with respect to alpha, it's continuous with respect to alpha. It is nowhere differentiable along alpha, which is the conclusion of my project.